Hello everyone. In our last class we have discussed basic things about refraction of the light. We discussed the laws of refraction and understood that what refraction means. So refraction, it is nothing but change in the properties of the light whenever it passes from one medium to the different medium. The medium is different in terms of its refractive index. Okay, then we have discussed what is relative and absolute refractive index of the medium, and then we come to know about the formula which relates the speed of the light in a medium with its refractive index, the refractive index of the medium, right? Then we have discussed the principle of reversibility of the light, and of course laws of refraction. All these we have discussed in our last class. So today we will discuss on the understanding what we have till now. Today we will discuss the refraction which is happening through a glass slab. So what happens to the light whenever it passes through a glass slab? Glass slab, it is nothing but a glass piece, rectangular or cuboid shaped glass piece, right? So here it is the diagram. This yellow color region, we are taking it to be a glass slab, and the light is entering this glass slab at one face of it, for example this, at point O. Outside this glass slab, the medium is air, for example, which is a rarer medium as comparison to the compared to the glass slab, medium of the glass slab, which is a glass whose refractive index is higher. Okay, so light ray, whenever it enters the glass at this interface, this is the first surface at which the refraction will take place, because at this surface, or we can say at this interface, the medium changes. So whenever light enters, comes from air medium and strike this interface at point O, the light undergoes change in its properties, just like its speed, its wavelength, and also its direction. So due to which it moves in this direction, the light ray bends slightly towards the normal, because light ray is coming from a rarer medium and entering a denser medium. So in that case, light ray always bend towards the normal. Okay, so this is angle of incidence here, and this is angle of refraction R1, right? So angle of incidence, we are taking it to be I1 here, which incident ray makes with the normal at the point of incidence, and this is the refracted ray which is moving in the denser medium. Now the angle made by refracted ray with the normal, it is called as the same normal, it is called the angle of refraction R1. Okay, so all these things we already know. Then what happens, this light ray again finds an interface at which again medium changes, and hence again refraction takes place. What is happening at this interface? The medium for this light ray is changing from glass, and again the medium is air, which is the same medium as the earlier one, right? So the light ray will move away from the normal whenever it crosses this interface. So it will bend away from the normal now, because now at this second interface, the light is coming from a denser medium and emerging in the rarer medium. So therefore light slightly bends away from the normal and makes an angle R2 as the angle of refraction at the second interface. Okay, at this interface, angle of incidence, we are taking it to be I1. From the geometry of the diagram, we see that I1 it is nothing but I2 it is nothing but equal to R1, right? So they are equal. Okay, so this is what is happening here. So we can have some basic discussion over this phenomena, that what result we are getting here. So we see that the light ray was coming from air. After going through the glass medium or any kind of medium, it again emerges to the same air medium. So what does it appear from the diagram? That the light ray is along its initial direction. It has the same direction as the original light ray was having. So this is incident light ray, this is refracted light ray, this is emergent light ray. Emergent light ray and incident light ray both are along the same direction. The difference is that the emergent ray is shifted. It is traveling at a perpendicular distance from the path of the incident ray. So this perpendicular distance by which the emergent ray travels now, this distance is called perpendicular distance. It is called as the lateral displacement or lateral shift. So our task is here to find out the value of this lateral displacement or shift whenever light ray passes through a glass medium and emerges again to the air medium. So this result will hold for all kind of media if this thing is happening. So at the first interface we are applying the one law of refraction, which is the Snell's law. It simply says the refractive index of medium B with respect to A means mu B refractive index of B divided by refractive index of A. So this is what it means actually. So this B is the medium which is in which the light ray is entering, and A is the medium from which the light ray is coming. Okay. So it is mu B upon A. This is always equal to sine of angle of incidence divided by sine of angle of refraction. So here in this first interface, the angle of incidence is I1 and angle of refraction is R1. So that's why we are writing it here. And whenever refraction takes place at the second interface, now the angle of incidence is I2 and angle of refraction is R2. So therefore now B is this air medium, right? So every time B is the medium in which the light ray is entering, right? And A is the medium from which the light ray was coming during the refraction phenomena. So it will be mu A B now. Mu A B, because light ray is traveling in now air medium while it was coming from the denser medium, right? So mu AB, this is equal to sine of angle of incidence, which is I2 here, divided by sine of angle of refraction, which is R2 here, for example, right? So now these two refractive index are just reciprocal of each other, right? As we have discussed during the principle of reversibility of the light, here principle of reversibility of light, from here we come to know this conclusion that refractive index of B with respect to A multiplied by refractive index of A with respect to B, it is always equal to 1, or simply it means the refractive index of B with respect to A, it is nothing but the reciprocal of refractive index of A with respect to B. So we are going to apply this thing here. So we are using this identity and substituting the values of these two here. So this will be equal to 1. According to the principle of reversibility, this is equal to 1. So we are setting their values. So this will be 1 only when these this R1 and I2 both are same, because they are the alternate angles, right? Okay. So these are the equal angles. So this will cancel out and will give 1. Only thing is left, sine I1 upon sine R1. So this will give 1. So this will be 1 only whenever numerator and denominator both will be same, which is possible only whenever R2 it is equal to R1. So that result, principle of reversibility of light, gives us that R2 it is equal to R1. Sorry, I1. So what does this mean? That angle of emergence, it is always equal to angle of incidence throughout the experiment. And if this is the case, then the final light ray, or we can say emergent light ray, will go parallel to the initial ray, or we can say incident ray. They will have the same direction. However, there will be shift in the path of the emergent ray. Light ray will shift by this much amount of perpendicular distance. So this is a very important result. Okay, so now our task is to find out this perpendicular distance, which is called as lateral shift or lateral displacement. So let us take this triangle. OQM. In this triangle, we are going to find out this angle delta. So from this, we know that I1, this angle will be I1 also, because they are the we can say opposite angles. This and this together are intersecting. These two lines are intersecting at point O. So if this angle is I1, this should also be equal to I1, out of which this angle is R1. So therefore this angle, remaining angle, will be I1 minus R1. So this delta, it is nothing but I1 minus R1. So in this triangle OQM, this angle is delta, or we can call it to be I1 minus R1. So we are going to find out the trigonometric ratio sine I1 minus R1 in this triangle, which is nothing but perpendicular upon hypotenuse. So perpendicular is given by Y and hypotenuse is OQ, right? So this is, now we have to find out the value of this OQ. We have to find out this value OQ in this expression, and then we can write the expression for the lateral shift or lateral displacement Y. In some books it is written as small d, so that makes no difference, only the change is notation. Okay, so to find out OQ, we use this triangle OSQ. This is also a right angle triangle, OSQ. So in this triangle, this angle is R1. So let us find out the value of cos R1 here. So cos R1 gives us perpendicular upon hypotenuse. So it is perpendicular base upon hypotenuse. So this is the base OS, or we can say it is the thickness of this glass slab, which we are taking as T, right, upon hypotenuse, which is OQ. In this triangle, again hypotenuse is same, OQ. So from here we can say that OQ, it is nothing but, from this equation we are finding the OQ. OQ is nothing but T upon cos R1. So this is what we get the value of OQ here. Let us substitute the value of this OQ from here to here and find the value of Y, which gives us this result, right? So this is the expression for the lateral shift Y. So from here Y, it is nothing but OQ sine I1 minus R1. Whenever we substitute OQ to be T upon cos R1, so it becomes T upon cos R1. So this is the expression for the lateral shift or lateral displacement, which takes place whenever light ray passes through a glass slab or any other medium. And this lateral shift will be more or less depending upon different factors, just like this. It will depend upon, number one, the thickness of the medium. More is the thickness of the medium, more this light ray will shift away from its original path. So more will be the lateral shift or lateral displacement, right? The value of angle of incidence, second factor on which the lateral shift will depend, it will depend upon the value of angle of incidence. More is the angle of incidence, more shift in the light ray will takes place. And third factor is the refractive index of the medium, of course, because it is the refraction due to which all this shift is happening. So more is the refractive index. I will preferably call it to be the relative refractive index of the two media, the rarer medium and the denser medium. It will depend more precisely on the absolute refractive, the relative refractive index of the two media, right? So these are the three factors on which the lateral displacement or shift of the light ray depends. Now we move to the next topic, which is about refraction happening through a compound plate. Now compound plate, it is nothing but, you can take it to be just like a set of different media, right? So we have one medium, for example air, then we have a denser medium, and then we have another medium of different refractive index again, which is even denser than this second medium, and then light ray again comes to the same rarer medium, for example air here, right? So what happens whenever light ray gets refracted through multiple media, you can also call it to be the compound plate, refracting plate. It is nothing but the refraction happening through a multiple media. So let me explain this by this diagram. So the light ray is coming from air medium and entering, for example, denser medium, for example, glass medium, right? So air is a rarer medium, glass is a denser medium. So light ray will bend towards the normal by making an angle of refraction R1. Angle of incidence is taken as I1. The refractive index of this rarer medium is mu A, right? So this is the refracted light ray. It keeps on traveling in this denser medium till it finds a surface, or we can say interface, which changes the medium for the light. Now the medium is changed to some other medium C, which is even denser medium. So light ray will again bend towards the normal slightly, right? So now this light ray is traveling in the third medium. Earlier it was traveling in the rarer air medium, then in the glass medium, then in this even denser medium, for example it is water. So it is traveling in this third medium, and then finally light again emerges to the same air medium. So we are indicating their angles of incidences and refraction here. So it is the angle of R1. So therefore this angle will be angle of incidence. It will also be equal to R1 because of geometry of the shape. And this is R1, the angle of incidence here. So angle of refraction here at second interface, it will be R2. So R2 will be the angle of incidence here at the third interface, and I1 will be the angle of emergence, or we can say angle of refraction at the third interface, which will be equal to the angle of incidence, as we have discussed in just previous article. So now we have to just apply the Snell's law at all the three surfaces. At first surface it will be light ray is coming from medium A to medium B, so therefore mu BA, it is equal to sine I upon sine R1. At this interface light ray is entering medium C, so therefore mu C upon B, or we can say mu C B, it is equal to sine of angle of incidence, which is R1 here, to the sine of angle of refraction, which is R2 here. And then at third interface light ray is coming to the air medium, so therefore mu AC, this is equal to sine of angle of incidence here, which is R2 here, divided by sine of angle of refraction, which is equal to nothing but I1, right? So this is, but the principle of reversibility of light says that this result holds here true. So the product of all these refractive indexes will, whenever light ray is coming from one medium and emerging to the same medium, so the product of the three will be equal to 1. If we multiply these, we will get 1. If we multiply these, we will get 1, because sine I1 will cancel out with this I1, sine of angle of R1, it will cancel out with this one, and sine of angle of R2, it will cancel out with this, and hence we can say that the product of all these three terms, refractive indices, will be equal to 1, right? So important conclusion that we draw from here is that howsoever different media are there to cause the refraction in the light ray, finally whenever the light ray will emerge to the same medium from which it was earlier coming or traveling, the light ray will have its own initial direction and it will emerge out at the same angle of emergence as the angle of incidence. And from here, whenever this term, third term, it is taken on the right hand side, it becomes 1 upon mu AC. Reciprocal of that is mu CA. So that is what is done here. So whenever this term is taken on the right hand side, it will be dividing 1. So it will be 1 upon something. Left hand side, it is the same thing, right? Okay. So it will be equal to 1 divided by just like this. Okay, so when this term is taken on the right hand side, it will divide this 1, and this 1 upon mu AC, it is nothing but the reciprocal of mu CA, so that's why it is written here. Okay, so from here we can write this expression in many forms. So from here, whenever this is taken on the right hand side, it will divide even further. So any of these can be calculated by using this expression. You must remember only the very first, it will be sufficient. So this is the second thing. One final thing here to understand is the phenomena of total internal reflection. So what is happening? So light ray, whenever comes from one medium and enter a different medium, it changes its path, and it also depends upon the angle of incidence. But one interesting thing happen here is that whenever light ray comes from a denser medium and try to emerge in a rarer medium, the medium of refractive index less than the denser medium, right? So what happens? Let us take this case. Suppose that this is a medium, a denser medium, glass medium, and outside it is the rarer medium, for example air. So here there is an object or source of light from where the light is coming. The light ray which is coming normally to the interface is nothing but the surface separating the two media. So normal incident light ray, it will go undeviated. However, change in the property of light ray will takes place. Okay. Whenever at this point in this situation, the angle of incidence is 0. So therefore angle of refraction is also 0. And in this case, whenever angle of incidence is increased from 0, more than 0, the light ray which is going to the rarer medium, it will bend away from the normal. It will bend away from the normal. It will how much it will bend, it will depend upon the relative refractive index of the two media and also on the angle of incidence. Whenever we increase the angle of incidence even further, so light ray coming from the same light source, for the larger angle of incidence, it will bend even more. So whenever we keep on increasing the angle of incidence for the light rays coming from this source placed in a denser medium, so the light rays are coming from the denser medium and angle of incidence is kept on increased. There will be one angle for which the light ray will go parallel to the principal axis. No light ray will enter the other medium, rarer medium, right? So this angle of incidence at which the light ray goes parallel to the interface or parallel to the surface separating the two media, this angle, it is called angle of incidence. It is called as the critical angle. And here the angle of refraction will be, you can call it to be the right angle, or we can say 90 degree. Angle of refraction at critical angle of incidence, it will be 90 degree. Whenever we increase the angle of incidence slightly more than this critical angle, the light ray will just get reflected back to the same denser medium. It will not go in the rarer medium. So such a kind of behavior of the light shown by the behavior of the light for an angle of incidence more than the critical angle, it is called as the total internal reflection. So it is the phenomena of complete reflection of the light back into the same medium. I would like to call same denser medium, right? Same denser medium for angle of incidence. This will happen only when angle of incidence is greater than some critical angle at for the medium. So this phenomena, it is called as the total internal reflection. It is a very important phenomena. It takes place in a number of we can say natural phenomena, just like a formation of rainbow, just like that, right? So the condition for total internal reflection to happen is that, number one, the incident ray must be in optically denser medium, or let me make it more simple, you can call it to be the light ray must be coming from a denser medium and from a denser medium and trying to immerse in a rarer medium. Or you can remember it by this: the incident ray must be in the denser medium, optically denser medium, the medium having the higher refractive index, right? So you can simply call the first condition to be the light ray should be coming from the denser medium and emerging to a rarer medium. Only then the phenomena of total internal reflection will happen. Second condition is that, which will together should follow, is that the angle of incidence, it should be more. The angle of incidence for the light ray in the denser medium, it should be more than the critical angle, right? So this angle will depend upon the kind of pair of media we are using. So these are the two conditions which must be simultaneously satisfied so that the total internal reflection can happen. So this phenomenon of total internal reflection is very important. So this angle of critical angle, it will how much will be the critical angle? It will depend upon the pair of media we are using, either air glass, water glass, or glass air, or water air, whatever set of media we are using. It will depend upon that. So we can, from there we can write the relationship between critical angle and the refractive index. So critical angle, it is that angle of incidence at which the angle of refraction is 90 degree, or we can say refracted light ray goes along the interface. So at that angle, the Snell's law again, mu a g, here a is air, which is a rarer medium, and g is the glass, which is a denser medium. So light ray is coming from glass to denser medium. So that's why we are writing it mu a g, this is equal to sine of angle of incidence upon sine of angle of refraction. Here refraction is nothing but 90 degrees, so sine 90 is 1. So, and at that angle, the angle of incidence, it is called as the critical angle. So we are writing it IC. So means this refractive index will be equal to sine of IC. So from here we can write, if we are willing to write the refractive index of the glass, you can write it by the reciprocal of the refractive index of the air. So refractive index of glass with respect to air, it is equal to reciprocal of refractive index of air with respect to glass. So from here, this term, which is sine IC, if we use this term, it will be 1 upon sine IC. It is simple. So you can write the value of this here. So you will get this expression, and this is the formula which will give the measurement of the critical angle. So why using this formula? If we know the relative refractive index of glass, which is with respect to air, which is called as the absolute refractive index of the glass. The refractive index of any medium with respect to air is its absolute refractive index, right? So by substituting the value of the refractive index of that denser medium, where we can calculate the value of critical angle. So this is the formula here, right? We can also find out this critical angle in terms of the wavelengths. So this is the wavelength of the light in the glass medium divided by wavelength of the light in the air medium, because refractive index and wavelength are related just like this. More is the refractive index, less will be the wavelength, shorter will be the wavelength. Okay. So that means the critical value of critical angle, it will also depend upon the kind of light we are using. Kind of light means the kind of wavelength of the light we are using. So there are very important meaning of total internal reflection, and its applications are very wide. So it is due to the total internal reflection due to which the mirage formation takes place, looming takes place. Total reflecting prisms are made for making optical devices just like binoculars, or we can say telescopes, right? Optical fibers, sparkling of diamonds. So all these phenomena happen only because of this total internal reflection. Because this phenomena is happening, we will take them one by one. in our coming classes. Thank you.